All right, so let's go ahead and draw an electric field. We have a charged particle inside that field, and we know that that field is going to do work, right? So it's going to do a certain amount of work, and it has a certain amount of charge. So if we take how much work in joules divided by the charge, we'll get voltage, right? And the potential difference as it goes across. Now, if we rearrange that, we multiply the voltage times the charge, and we get the work, as it brings it across. Power is how much work we do in time. So if we place that in there, we have voltage and we have Q. Electrical power then is the power dissipated in the resistor in moving a charge Q across the resistor in time t. And so this is a technical definition that you're going to want to write down. We did this in the fall, but again, it's not so intuitive in terms of something easy to remember. I think it's something very specific we need to look at again. So now this should kind of make sense. It's a power dissipated or used up in the resistor and moving charge Q across it in time t. And that's how we eventually end up getting then voltage times current, which we've used quite a bit. And so, yeah, so that's a critical thing there. Now, EMF, we're dealing with a cell, and so we're looking at how much work done per charge. If we divide the top and bottom by time, we get work over time, Q over T, which is power per current. So EMF is the power provided by a battery per unit current. Another technical definition that comes from a lot of the things that we've done. Work done per or power per unit current, right? So the work done on a charge over a period of time, and then charge over time, which is current. And so, yeah, another one that you'll just want to remember. All right, lattice ions are another thing that's important there too. And so, yeah, go ahead and pause the clip and read the caption here. This should be a good reminder for us. And then when you're ready to continue, hit play. All right, Ohm's law, right? So we use this so much this year, and it's very important. Current is inversely proportional resistance. You have more resistance, you have less current, and it's inversely proportional. You have more voltage, you're going to get more current as long as something is ohmic, right? And the resistance doesn't change, and it's not like a light bulb. So what kind of energy transfer is in a cell or a battery? Oh, it's chemical to electrical, right? You have the chemical reaction, and then you get the electricity. And the voltage that we get from this is EMF, electromotive force. All right, so one of the things that is critical here as we look at cells is, how much practical, voltage are we going to get out? Now we have, the internal resistance that is causing some of the, voltage not to be as much, useful voltage, and that's used up in the battery. And so, it's right internal into the battery. One of the things that can be very helpful for us if we're working through one of these is, if we set up, let's go ahead and set up this here. So we have a 12-volt cell. The internal resistance inside there is 0.12 ohms, very small. We have a 4 ohm and a 7 ohm resistor in series. How much voltage is used up in the battery? How much is used up? So yeah, so we can find that out by looking at this as being a series circuit, right? We have the first resistor, second resistor, third resistor. So what we do is we bring it all together. We can apply Ohm's law, figure out what the current is, and then we break it apart and we say, okay, how much voltage is used inside here? And then we can subtract that from the total amount. So go ahead and pause the clip and do that series circuit and see how much is used up inside the battery, and then when you're ready, or in the cell, and then when you're ready to check, you can hit play to continue. All right, so bring them all together, 11.12 ohms, and we should get 1.079 amps. So therefore, when we apply Ohm's law there, it's going to use up 0.129 volts. So that 12-volt cell is we're going to have to subtract that out to get, the useful voltage, from because that's going to be taken up. And that internal resistance has to do with the chemical reactions in the battery. It's not instantaneous, right? So even though you got the potential there, it's not going to be an instantaneous thing. And so we've got some internal resistance in that cell.